Today I'm going to show you how to use orbital notation. Orbital notation is just another way of representing the electron configuration of an element. So it shows where the electrons live in the atom. So this first slide is the general layout of the orbital notation diagram. Now this shows all the possible levels, but if your notation, say, only goes up to here, then you don't need to draw any of these other lines in here. Okay, first thing I want you to notice is that energy increases as you go up. So this sublevel, 1s, is the lowest energy, which we already knew that because it's the first one on the top left of the periodic table. Okay, so as you get farther and farther up, energy is increasing. One thing I want to point out is this little tricky spot in here. 3D is actually less energy than 4P, right? So anytime it's higher, it's going to be higher energy. The other thing I want to point out, notice that all of your S sublevels only have one line over them. That's because they have one orbital. They have one orbital and house 2 total electrons. Your P sublevel has 3 lines on it. That's because they have 3 orbitals and hold a maximum of 6 electrons. Your D sublevels have 5 orbitals and therefore hold a maximum of 10 electrons. And your F sublevel has 7 orbitals and therefore holds 14 electrons. Okay? So it should all look very familiar. What I'm going to do first is go over the rules of doing these diagrams. Then I'm going to do a few with you. So, the first rule you have to follow in writing these orbital notation is the Pauli exclusion. All the Pauli exclusion rule is 2 electrons in an orbital must have opposite spin. Must have opposite spin. How that's represented in these diagrams is by arrows. So for example, if you have a S sublevel, you could draw the electrons this way, or you could draw the electrons this way. Okay? So this one breaks the rule because they're spinning the same direction. This one is how we do it. You always want them to be flipped opposite. So electrons are represented as little half arrows in these diagrams. So you want them to be opposite. Cool. Easy enough. The second rule, the Aufbau rule, is that orbitals are filled from low to high energy. From low to high energy. Meaning the electrons are going to take homes in the low energy orbitals before they move to the high energy. We've been doing that all along. You go through the 1s and the 2s before you get into anything else. You never just jump straight down to like 5s and then go backwards and fill ones that are smaller. So you always start with the lowest energy levels first. And Hund's rule, the last one. 1 electron fills each orbital of a sublevel of a sublevel before doubling up. Okay, so 1 electron fills each orbital of a sublevel before doubling up. So let's say we have a P sublevel. So a P sublevel has 3 orbitals in it. Okay, so if we were to be drawing in our electrons here, let's say we had 4 electrons in it. 1, 2, 3, 4. Okay, so this is the incorrect way of doing it because we didn't put 1 in each orbital before we started doubling up. So in this one, I put 1 in each orbital, and then I went back to the left and started doubling up. So this would be the correct way of doing it. You always put 1 in each before you start doubling up. Okay, so what we're going to do now is go through a couple notations that are already filled out and see if we can find the mistake in the notation. See if we can find which of these rules were broken. Okay, so find the error, oxygen with 8 electrons. So 2, 4, 6, 8. This guy has 8 electrons, so we're good to go with that. So if you look, they all are facing the opposite direction like they're supposed to, but there's 4 here and there's nothing in here. So this actually breaks the last one. This breaks Hund's rule. Okay, this breaks Hund's rule. So what it's supposed to look like, 2, 3. 1, 2, 3, 4. Okay? So this is what that last one is supposed to look like. Cool. Easy one. Okay, find the error. Potassium with 19 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 19. We're good there. Looks like they're being filled from low to high like they're supposed to. They don't have any, they have 1 in all orbitals before they double up. So here's our problem right here. These guys are moving in the same direction. So this breaks the Pauli exclusion rule. The Pauli exclusion rule. They need to be moving opposite directions. So this is supposed to look like this, right? It's supposed to look like this. Okay, so there's that one. And one more example. Okay, titanium with 22 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 22. There are 22 here. All of them are facing opposite directions. So let's see where they end. This element ends at 4p2. 4p with 2 electrons. So let's look on the periodic table and see where 4p2 falls. So these are my p groups. 2p, 3p, 4p2 is right here. Well, that's not titanium, so there has to be an error. Let's go back and see if we can find it. Okay, so your problem is right here. Okay, so you don't fill from left to right. You're going to fill from top to bottom. So this one is actually farther down than 4p. So these 2 electrons need to go in here. So this is the Aufbau rule. Whoops. Whoops, it's not writing very well. Aufbau. This is the Aufbau rule that's being broken. Okay, so now that we moved these, our last group here is 3d2. So let's see if titanium is in 3d2. This is my D group, this is 3d, and 3d2. There it is, titanium. Looks good. Okay, so those are the most common mistakes that can be made that you want to look out for. And those are the 3 rules that you want to make sure you're doing correctly. Okay, so using those rules, let's try to do our first orbital notation. So you start on the bottom row. We want to draw in electrons facing opposite directions until we add up to 17. So that's 1, 2, 3, 4, 5, 6, 7. Notice I went all the way through before doubling up. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so that brings us to 17 electrons. Looks good. So what I want to do now is quickly draw up the electron configuration of chlorine so you can see how these 2 diagrams, or how this diagram compares to the electron configuration that we already know how to do. So 2p6, 3s2, 3p5, So 6, 7, 8, 9, 10, 11, 12, 17. Okay, so you don't have to look too closely to see the pattern. They're exactly the same. My 1s level has 2 electrons in it. My 2s level has 2 electrons in it. My 2p level has 6 in it. So it goes in the exact same order than it would go in your electron configuration, and that's 2, 4, 5. Okay, so you should be able to work between these two configurations or these two representations. If you have one, it should be pretty easy to figure out the other one. Let's do another example. So it says convert to electron configuration and identify the element. So if I'm converting to electron configuration, I'm just going to write them from bottom to top. 1s, and I see 2 in there, 2s2, 2p6, 3s2, 3p6, 4s2. This is where it gets tricky. You want to go all the way over here because it's below 4p. 3d10, and finally 4p2. Okay, there's two ways to figure out what element you're dealing with here. One of the ways is to add all these up. 2, 4, 6, 12, 18, 20, 32. So you can find element number 32 to figure out what element you have, or the much shorter version is to look at your last one, 4p2, and just go find 4p2 on your periodic table. So let's find 4p2. So this is my P group. This is P2, P3, P4. So 4p2 lands us right on germanium again. So the element is germanium, and you'll also see that the atomic number is 32, which is what we calculated. So this is germanium, right? Not so bad. Electron configuration is the hard thing. Once you've learned it, these orbital notations are pretty darn easy. Okay? All right, so those are the only examples I'm going to do today. I will see you next time.